Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 7 of the series on linear relations, and we will be discussing some elementary characteristics of a circle. And yes, I do know that a circle is nonlinear, but I will be presenting these ideas in this series anyway. The first thing I did over here is I chose a point and I called it the origin. That would be City Hall if you're located in Toronto. And then what I did was I went to one of these quadrants. This is called quadrant 1, quadrant 2, quadrant 3, quadrant 4. I went specifically to quadrant 1. And I chose a center for the circle. So how did I get there? I went A units to the right and B units up so that the coordinates of the center are A comma B. And then what I did was I took a huge compass. I put the metal pointer of the compass at the point C, and I extended the compass through a radius R, and I had the pencil drop at the point P. I made sure that the radius was fixed. I made sure that the center was fixed. And then I took the compass and I rotated it left to draw a nice, hopefully perfect circle until you get back to the point P. Now, what was necessary in drawing that circle? It was absolutely essential that the center did not move. In other words, the pointy part of the compass did not move, and the radius remained fixed. So the radius has to be constant, and the center must be constant in order for you to generate a perfect circle all the way around. Next, we turn our attention to going from the center to an arbitrary point P on the circle. The point P will in general have coordinates x comma y. So let's pretend for one moment that we knew what the coordinates were for this point. We'll call them x comma y. Then we look at the point Q. If you look at the point Q, it'll have the same x coordinate as the point P, but the y coordinate will be the same as the y coordinate of the point C. Okay, so the coordinates of the point Q are x comma b. Now, let's see if we can figure out how to calculate the run going from C to Q. Okay, you know the run is x2 minus x1, but x2 is just x and x1 is a. Okay, so the run would be x2 minus x1, which is x minus a. And also, let's see if we can figure out how to calculate the rise. We know that the rise is y2 minus y1. So it's y2 minus y1. So in this case, we have y minus b. So we get a run of y minus b. So now we've identified the run for triangle CQP and the rise for triangle CQP. We have a nice little right-angled triangle here. That means that we can apply the Pythagorean theorem to this triangle. The Pythagorean theorem says that run squared plus rise squared equals hypotenuse squared. So run squared plus rise squared equals hypotenuse squared. When we restate that, that really says that x minus a squared plus y minus b squared equals r squared. Again, delta x squared plus delta y squared equals the hypotenuse squared. And this is exactly the equation of a circle. Okay, so every point on that circle P with coordinates x comma y must satisfy this relation. This defines the equation of a circle in standard form. R is the fixed radius, and C is the fixed center. Now, of course, as you vary the radius, the circle will expand or contract. If you change the center, the circle will translate to any other point in the xy plane. So the center serves as a translator, and the radius either serves as an expander or a contractor. At any rate, we have three parameters. A, B, and R will define this circle. So as soon as you figure out what A, B, and R are for your particular circle, you've essentially defined the equation of the circle, and the circle is fixed. Now, a few other things over here. You'll notice that this particular circle cuts the x-axis at the x-intercept here and the x-intercept there. It also cuts the y-axis at the y-intercept here and the y-intercept here. Okay, so now if the radius is fixed and we move the center outwards, eventually the y-intercepts won't exist and the x-intercepts won't exist either. Why? Because we haven't changed the radius, we just picked up the center and moved it further out. So eventually the circle will not cut the coordinate axes at all. Okay, so we can't tell right away whether a circle does indeed have x and y intercepts. That's something we need to test out. Okay, x equals a is just the vertical line passing through the center, and y equals b is the horizontal line passing through the center. And just a few more things. Y min, which is the smallest y value, is in fact b minus r. The y value of the center is b, and of course this is the radius r. So y min is actually b minus r. And let's look at y max over here. Y max is b plus r. B is the y coordinate of the center, so b plus r will be this height here. Okay, so altogether y max is b plus r. So we go to b and then plus r will get us up here. For the other one, we go to b and then minus r will get us down there. Also for x min, we start off at a and minus r will get us to x min is a minus r. Again, we start off at the center. We go to this point over here, so we start off at a and go to a plus r. And that's why x max is a plus r. So to recap, x max is a plus r, x min is a minus r, y max is b plus r, and y min is b minus r. Okay, there's nothing else to discuss on this slide, so we'll turn to the next slide. In the next few slides, we'll be running through some elementary questions regarding circles, and we'll be starting with Q10. And they give us the equation of a circle in standard form, bracket x minus 2 squared plus bracket y plus 1 squared, a sum of squares, is equal to 18. And that certainly defines a circle in standard form. And part 1, they want us to find the center of the circle. And we know that the center of the circle is a comma b. And how do we identify a comma b? We identify it as the opposite of the numbers inside the brackets. The opposite of negative 2 is 2. The opposite of 1 is negative 1. So that means the center with general coordinates a comma b in this specific case becomes c with coordinates 2 comma negative 1. So the opposite of negative 2 is 2. The opposite of 1 is negative 1. And that would be the answer there. So that was very easy to do. Identifying the center of a circle from its standard form. And then part 2 over here asks us to find the radius of the circle. Now, of course, the radius of a circle is just the square root of the right-hand side of the standard form. We have the standard form right here. The right-hand side is identified as 18. So the radius is the square root of the right-hand side, which is the root of 18, which can be decomposed as root 9.2, and then the square root of 9 is 3, so we get 3 dot root 2. So we conclude that the radius is 3 root 2. So that was a fairly simple question on identifying the center and the radius using the standard form for a circle. We'll turn to the next slide. For the same circle, they want us to identify the x and y intercepts. Okay, because they're so what I did was I drew a 2-column t-chart, and I talk about the x-intercepts on the left and the y-intercepts on the right. Okay, now the intercepts may or may not exist. Okay, so we'll find that out in a minute. To find the x-intercept, you set y equal to 0, because the x-intercepts are points on the graph whose y-coordinate is 0. Similarly, the y-intercepts are points on the graph where the x-coordinate is 0. So we set y equal to 0 in the standard form. There's the standard form right there. We set y equal to 0. When we do that, we get x minus 2 squared plus 1 equals 18. We move the 1 over to the right-hand side, and we get x minus 2 squared equals 17. We take the square root of both sides, and don't forget the plus or minus when you're taking the square root now, okay, because we're not doing distance here. Okay, so don't forget the plus or minus when you take the square root of both sides. The square root of the left-hand side, because it's a perfect square, is just the inside of the brackets. We get x minus 2. And of course, on the right-hand side, we have plus minus, the square root of 17. And we bring the negative 2 over to the right-hand side, and we get x equals 2 plus minus root 17. And we conclude that we have 2 x-intercepts. We'll do the same sort of thing on the right-hand side over here to identify the y-intercepts. We're going to be setting x equal to 0. So again, we get the same standard form that was in the previous slide, and we set x equal to 0. There's the x right there. When we do that, we get negative 2 squared, which is 4. And of course, this is just a drop down, and 18 is just a drop down. In the next move, we bring the 4 over to the other side. 18 minus 4 is 14. And at this stage, we have a perfect square on the left. So we're going to take the square root of both sides. The square root of the left-hand side is just y plus 1. And on the right-hand side, you write down plus minus square root of 14. So don't forget to put the plus minus in front of the radical on the right-hand side. All we have to do is move the 1 over to the right-hand side. It becomes negative 1. And we conclude that y equals minus 1 plus minus root 14. And these are the 2 y-intercepts. Okay. Notice that the x-intercepts over here are conjugate radicals. 2 plus root 17 and 2 minus root 17 are called conjugate radicals. And the same thing for the y-intercepts. We get y equals minus 1 plus minus root 14, and these are called conjugate radicals as well. Minus 1 plus root 14 and minus 1 minus root 14 are conjugate radicals. We next turn to question 11, and it says finding the equation of a circle when you are given the center and a point on the circle. So if we're given the center of the circle and any other point on the circle, what is the equation of the circle? That's what we're trying to find out. So in this case, we're given that the center, which is generally a comma b, the center in this case is minus 2 comma 3, and a point on the circle will have coordinates 3 comma 4. So this is given information. Anytime I write down the word data, that means that this is what's given in the problem. And the objective is to find the equation of the circle. Well, we know what the standard form for any circle is. It's x minus a all squared plus y minus b all squared equals r squared. Okay? And now all we have to do is substitute in the center. A comma b is minus 2 comma 3. And x comma y is 3 comma 4 for the point. When we do that, we get 3 plus 2 all squared plus 4 minus 3 all squared equals r squared. When we simplify the left-hand side, and we immediately obtain that r squared equals 26. All I did is switch the order. I flipped the equation. And you get r squared equals 26. I didn't move anything. I just flipped the equation about the equal sign. Okay, so I got r squared equals 26. And you know the radius is positive. So you're going to take the square root of both sides over here and conclude that the radius is the square root of 26. Okay, and the square root of 26 is in reduced form. So I put rf over here. Don't forget that when you're trying to find the radius, it's no longer plus or minus. It's not like finding the x and y intercepts. Okay, when you're finding the radius is defined to be a positive number, and it will always be a positive square root. And now all we have to do is go to the equation. There's the general standard form, and we insert a comma b is negative 2 comma 3. And we know that r squared is equal to 26. We just perform all those substitutions and immediately get bracket x plus 2 squared plus y minus 3 squared equals 26. And lo and behold, we have the equation of the circle in standard form. Okay, let's have a look at the next slide. This is a little note over here on testing whether a given point is inside the circle, on the circle, or outside the circle. Okay, so what they're going to give us, they're going to give us a point, let's call it P1. So this is a fixed point. This is a test point. It'll have coordinates x, y, y1, so that will be given. That's the given test point. Think about that as being a dart. And then we have the perimeter of the dartboard will be the equation of the circle. Okay, so the equation of the circle in general is x minus a squared plus y minus b squared equals r squared. And so that circle will be given. And it has center a comma b, and of course the radius is r. And we'll declare that to be the perimeter of the dartboard. So you're given the dart, you're given the dartboard, and you want to find out whether the dart is actually inside the dartboard, on the perimeter of the dartboard, or outside the dartboard. That's essentially what we're trying to do. And we have a simple test for doing that. Test for location of P1 relative to the given circle. Okay, we know what x1 is, we know what y1 is, we know what a and b are. This is the left-hand side of the standard form. Okay, so we know this number. We know what a and b are. That's just the center of the circle. We know x1 and y1. Those are the coordinates of the given point or the dart. And we want to figure out whether the dart is inside, on, or outside the dart. So this will be a number that we will know. And also the radius squared is known from the standard form. Now, when we plug in these numbers and crank out this sum of squares, three things can happen. It's either less than r squared, and we conclude that P1 is inside the circle. It could be exactly equal to r squared, and we conclude that P1 lies right on the circle. Or it could be greater than r squared, in which case P1 is outside the circle. It's a very, very easy test. Less than, inside, equal to, on, and greater than, outside the circle. So if it's less than r squared, the dart hits the dartboard. If it's equal to r squared, you're right on the perimeter of the dartboard. And if it's greater than r squared, you're completely outside the dartboard, and you need more practice, obviously. So let's go on to the next slide. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.